Okay, so today is day 3, and we're going to talk about repeated items. We're also going to look a little bit at the difference between linear and circular permutations. So let's start today off right away with an example. So how many different ways can the letters of the word arrangement be arranged? So, we kind of look at this as a permutation, but there's a little something special we need to look at. So we're going to look at the idea. Let's remove these R's real quick. So let's write A, N, G, E, M, E, N, T. And I'm going to do one of the R's in a blue here and another R in green. So we have the word arrangement. And I'm just denoting those two R's so we can tell the difference between them. But if you really think about it, there is no way to tell the difference between which R we put in each spot. So what that means is, if I were to rewrite this, duplicate that, and we'll erase our R's again, and switch the spot where the blue and the green R is, I haven't actually changed the arrangement. All I did was switch those two R's, but that does not make a different arrangement because we cannot tell the difference between the same letters. Same thing would go if I were to switch this first A with the second A and the second A with the first A. It would still be the same arrangement of letters. Okay. So we do have a formula for this. Okay, and that's the formula down below. You take into account how many total letters you have. So that's your n factorial. So in this case, in arrangement, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have 11 factorial. And then on the bottom, you got to take into account your duplicates. So, where all my R's could go, I could also flip them. But we don't want to have that, so we need to take that away. So we divide by those duplicates. So for R, there are 2 of them. So for R, it'd be 2 factorial. That is to divide and remove those repeats. Okay, A repeats, we have 2 A's. So it'd be 2 factorial for your A's. Okay, and then the best way to do it is just start with the first letter and go through this. We got our A's done. We got our R's done. N has 2. So again, 2 factorial for our N's. G is good. And then E, we have 2. Okay. So we can just go to our calculator for that calculation there. And we do find that to be a rather large number. Okay, and that turns out to be 2,494,800. Okay, now that's taking into account that A, R, and E are not distinguishable. If we could make them distinguishable and actually had different colors, that number would skyrocket a lot more. Okay, so let's look at another example. Let's talk about the word Mississippi. Okay, so again, we want to figure out how many total letters we have in Mississippi. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So again, we're going to have 11 factorial. And then we're going to go through our letters. So we have M. There's only one M. Okay, you don't need to put 1 factorial on the bottom. We go to our S's. We have 1, 2, 3, 4 S's. We have our I's. We have 1, 2, 3, 4 I's as well. And then we have 2 P's. Okay, so it does not matter the order that I have them there at the bottom. Okay, that could be 2 factorial, 4 factorial, 4 factorial. Whichever order that I would want to have those in would be perfectly fine. And we see that there are 34,650 ways to rearrange the word Mississippi. And you'll notice the last word also had 11 letters, but it had a lot more ways for arrangement. And again, that comes in the fact that not as many letters repeated in arrangement. Here's a little bit trickier of a problem. How many different ways can the letters of Mississippi be arranged if the 2 P's cannot be together? Okay, so what we're going to do here is we're going to remove the P's. Okay, and then we're going to have to be putting them back in different places. So I have M, I, S, I, S, S, I, I. Our P's are going to have to go somewhere in these spaces. The P could go before the M, it could go after that last I, it could go in between any of these letters. So if you think about it, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 spots for these letters to go. And I need to pick 2 of them. Okay, so that's a combination. How many different ways can I pick those 2 spots to place my P's? Okay, so we're going to have 10, choose 2. That's going to give me all the spots that the P's could go, the different ways. But then I also need to take into account the different arrangement that these other letters I have left can go. Okay, my M, I, S, S, I, S, S, I, I. So that's going to go back to what we did before. Okay, where we had 9 letters, so 9 factorial. And I do have to look at the ones that repeat. So in this case, the I repeated 4 times. And the S is repeated 4 times. Okay, and this is how I would end up getting my answer. So again, it's the ways in which I can place the 2 P's in those 10 spots. And then it's the number of ways the other 9 letters can be arranged into different orders there. So our answer for this one, if you go in there, the 10 choose 2 would be 45. Okay. And the other half here would be 630. And that gives us a total of 28,350 different ways. Okay, next little bit we have here is linear versus circular permutations. So the first problem we've done before, how many ways can 3 people be seated in a row? Well, let's going back to our slot method. So you have your 3 spots. I can obviously put 3 people in the first spot, 2 people in the second spot, and then I have my leftover person at the end. So there would be 6 ways for these people to be seated in a row. But now that problem changes if I'm going to sit people at a table. Okay, so let's get started here. We're just going to draw circles. Okay, and there's going to be 6 of them, right? Because you're going to think about, the orders that we had before. Yeah, so the first example, we'll put person 1 at the top seat, 2 and 3. Okay, the other way, I could have the 1 at the top, the 2 on the left, the 3 to the right. Okay, we'll bring 2 to the top, 1 on the left or right, 3 on the left. And then flip those. And the last one, we'll put 3 on top, 1 and 2, 2 and 1. So it looks like there are 6 ways again. But we got to take into account that we're at a table, a circular table. If the rotational is the same, then they're really the same order in which people have been seated at a table. So if I look at this example here, this goes 1 to 2, 2 to 3, and back to 1. Right? So if I follow in that rotation, okay, 1 to 2 to 3. Okay, let's see if we go to any other ones. Well, this one here, I could go from 1 to 2 to 3 and back. And then this other one down here, going clockwise, 1 to 2, 2 to 3, 3 to 1. So all 3 of those are actually the same. It's just been rotated. If I go to this one, follow that order, go 1, 2, 3, it's going counterclockwise. 1 to 2, 2 to 3, and back. 1 to 2, 2 to 3, and back. It's just going the opposite. So they're rotational symmetry. They're duplicates. So really when we look at this, we only have 2 different ways in which people could be seated at the table in which we would be able to tell the difference there. Okay, so anytime you run into a circular permutation to arrange n items in a circle, okay, we can use n minus 1 factorial. So in this case, it would have been 3 minus 1 factorial, which is 2 factorial. 2 times 1 is 2. You could also very quickly do this just by thinking, okay, for the 1, the 2 is to the right, the 3 is to the left. And here, the 2 was to the left and the 3 was to the right, and then you can figure out your way there. So we're going to move on and talk about this next example here. We're going to sit 18 students in a circle. How many different ways could they sit? Okay, well, here's your 18 students. So it is just going to be 18 minus 1 factorial, which is 17 factorial, which will end up being a pretty large number for us here. Very, very large number. And now when you get something like this, you would be perfectly fine if you wanted to just leave it as 17 factorial as well. Then you don't have to worry about writing any numbers wrong on there or putting anything in the wrong spot. Now, there's something else you have to be careful with. Let's revisit our 3 people sitting in the circle, but we're going to consider 3 different colored beads. So we're basically making a bracelet. So again, let's get our circles here. Okay, so we'll go, let's get green. We'll put green up top first. We'll do blue to the left this one, blue to the right there. Actually, that's not even a good blue. Let's change that color. Let's make sure we get a nice dark blue. And then red. Okay, now let's put red on top. We'll put green left, green to the right. And then we'll put blue right and left. And then finally, we'll put blue on top. Red to the left and right. So again, these are our same examples from above. So we already saw that there are 2 different orders here, right? Now, if we really focus on it, we could going clockwise. We could have green to red, red to blue, blue to green, right? So we went G, R, B. 3 of these follow that order, and 3 of them follow going green to blue to red. Now, let's look at those 2. Let's look at just those 2 specifically. If I were to take this bracelet and just flip it over, so it's still the same bracelet. So if I were to take this bracelet up top, and then all I do is flip it over, the blue would go to here, the red would go to there. And what I would end up with is the exact bracelet down below. Okay, so since this bracelet is able to be flipped, okay, these are actually the same bracelet. Okay, which means I can make all 6 of these patterns out of the same bracelet just by flipping it or rotating it. So in any case that you are allowed to flip, now if you think about it, I'm not flipping people on a table. Okay, the table itself cannot be flipped, so that would only have rotational symmetry. I use the formula n minus 1 factorial divided by 2. So let's see if that holds and gets our answer of 1 from above. So n minus 1, 3 minus 1 factorial over 2. 2 factorial, which is just 2 over 2, is 1. So there's only one bracelet that we can really make here. Yeah, our last and final example. How many ways can 7 keys be arranged on a key ring? Okay, so if you think about the ability to flip here, Okay, it's basically looking at your bracelet by rotating, okay, or by flipping my keys, I can create the same key ring. Okay, so let's see how many different ways there are there then. So if n is 7, it's going to be 7 minus 1 factorial over 2. Okay. So 6 minus 1 factorial, so 6 factorial over 2. 6 times 5 times 4 times 3 times 2 divided by... We see there are 360 different key rings that we can create here. Okay, so you got to take into account, like there are still the different orders in which you have them rotational. So by switching a rotational order will change it. But then you got to remember some of those rotational orders